Dear friends, today we will see the example number 10.6 of exercise of chapter number 10. The information is given like this. A beam of light consisting of two wavelengths 650 nanometer and 520 nanometer. So we are given lambda 1 as 650 nanometer. So it is given 650 nanometer, that is 650 into 10 raised to minus 9 meter, and another wavelength, that is 520 nanometer, that is 520 into 10 raised to minus 9 meter. These two wavelengths. Now this light is used to obtain interference fringes in Young's double slit experiment. So here the case is of Young double slit experiment. So we are asked to find out first what we have to find out. Find the distance of the third bright fringe on the screen from the central maximum for wavelength 650 nanometer. And second, what is the least distance from the central maximum where the bright fringe due to both the wavelength coincide. The distance between the two slits is 2 millimeter. So here they have given the slit width, that width of slit, that is 2 millimeter, that is 2 into 10 raised to minus 3 meter. So we can say that here D is equals to 2 into 10 raised to minus 3 meter. So that is given a slit width, and the distance between the plane of the slit and the screen is 120 centimeter. So distance between slit and screen, say capital D, is given by 120 centimeter, that is 2 meter. Sorry, 1.2 meter. So you can say that it is about 1.2 meter. So now first we will apply our general knowledge on the basis of the question, that to find out the third bright fringe, that means we have to find out third bright fringe. So that for answer A, third bright fringe that is n is equals to 3, third bright fringe. So we can say x3 is equals to n, or we can go in a general way. So first we will write general equation, that is xn is equals to n lambda d over d, that is your basic equation for nth bright fringe to find out. So we can say that here we want to find out third bright fringe. So x3, that we will put 3, lambda for 650, so it is 650 into 10 raised to minus 9. We are given capital D as 1.2 meter, and small d is a 2 millimeter, that is 2 into 10 raised to minus 3 meter. So ultimately this will be, when we simplify, it is clear that it will come out to be 1.17 into 10 raised to minus 3 meter. So the solution will be, that is, the third bright fringe will form at 1.17 millimeter away from the central maximum. Now another question that they have asked, that where they both will coincide. We say that suppose at any distance, say x, from the central maximum, we can have same intensity, or that the coincident point of them. So we say that suppose at distance x from central maximum, we will have, that is, x is equals to n1, beta 1 is equals to n2, beta 2. Now we want to understand that obviously the condition is as it is. So we can say now that here the condition for n1, that is say n, and d lambda 1 over small d is equals to n2 d lambda 2 over small d. Now from this condition, capital D and small d are same, and therefore they will be cancelled out. So we will have n1 lambda 1 is equals to n2 lambda 2. Now the bright fringes will coincide at least distance, say x. So if so, we can say that the bright fringes will coincide at the least distance, LEST, least distance x, if they are in the condition that n2 would be n1 plus 1, and therefore n1 lambda 1 is equals to n1 plus 1 lambda 2. Now we have all the lambda 1 and lambda 2 in our condition, so we can simplify this equation and get the condition, that is n1 plus 1 over n1 is equals to lambda 1 over lambda 2. Now this will give us n1 by n1 plus 1 by n1 is equals to lambda 1 over lambda 2. So we can simplify this equation. When we simplify, we get again, that is 1 plus 1 over n1 is equals to lambda 1 upon lambda 2. Therefore 1, or we can keep it like this, that is 1 over n1 is equals to lambda 1 upon lambda 2 minus 1. Now if we simplify it more, then 1 upon n1 is equals to lambda 1 minus lambda 2 over lambda 2, and if we make the subject, that is n1, to be a subject, we can say that n1 is equals to lambda 2 over lambda 1 minus lambda 2. This will comes out to be simply lambda 2, that we have 520 into 10 raised to minus 9. Here this is 650 minus 520, so here this will be 520 over 130, and we can have therefore 4. So n1 will be the answer as a 4. Now from this, the required distance, if we want to find, so from this the required minimum distance from central maximum will be x is equals to n1 lambda d over capital D. So here n1 will be 4, lambda 1 will be 650 into 10 raised to minus 9, capital D is 1.2, and small d is 2 millimeter, that is 2 into 10 raised to minus 3. So now when we simplify this, we get that is 1.56 into 10 raised to minus 3, that is 1.56 millimeter. So that's it from the example number. The next example, that is example number 8, that is what is Brewster's angle for air to glass transition. So actually this question is good for your exam. Here there is a very simple equation that we have to use, that Brewster's law is the one equation, that is that example number 8. I can explain that Brewster's law belongs to that mu is equals to tan angle of polarization. So we can say that here the refractive index of glass is given, and therefore what is Brewster's angle for air to glass transition? We can find out the IP. We can say that for glass mu will be 1.5, and therefore that tan IP that will be 1.5, and therefore IP would be tan of inverse 1.5. Going to the table, we can say that this will be 56.3 degree. So this is the Brewster's angle for that is air to glass transition or light. Now we will see an example number 10.9 of exercise chapter number 10. Now in this example, what is been asked and what is been given, they have given us that light of wavelength 5000 angstrom. So we have provided here lambda, that is 5000 angstrom, that is about 5 into 10 raised to minus 7 meter. So they have given that is 5000 angstrom wavelength light falls on a plane reflecting surface. What are the wavelength and frequency of the reflected light, and for what angle of incidence is the reflected ray will be normal to the incident ray? So here we are given simple things and we are asked simple thing. Question is clear that speed of light is fixed in a given medium and frequency of light does not change during its reflection from surface. Consequently, the wavelength should also remain unchanged. So the speed of reflected light, first question, that speed of reflected light will be exactly equals to speed of incident light, and that is clear for air, that is 3 into 10 raised to 8 meter per second. Now wavelength of reflected light is also the wavelength of incident light, so it will be true for the wavelength also. For wavelength also it is true, and therefore for the reflection lambda reflected will be equals to lambda incident, and that is given 5000 angstrom, that is 5 into 10 raised to minus 7 meter. So these two information are given or we have considered. Now we can say that we have one very well known equation, that C is equals to lambda f for the wave nature of any object. Here f belongs to frequency, so the frequency of the light will be C over lambda, that is 3 into 10 raised to 8 over this is 5 into 10 raised to minus 7, and if we consider and simplify it, we can have f is equals to that is 6 into 10 raised to 14 hertz. So that will be the frequency of the light. Now another information that we have from the law of reflection, that we can say that by the law of reflection we can say that angle of incident is equals to angle of reflection, and therefore here they have asked that I plus R to be a 90 degree, and therefore angle of incident is equals to angle of reflection is equals to 45 degree. That will be the answer in our case. That's it from the chapter number 10.